So let's look at the first property of Hermitian and skew Hermitian matrices. First property says that, so if A is a Hermitian matrix, if A is a Hermitian matrix, that implies Ka is a Hermitian matrix if K is a purely real number. So if A is a Hermitian matrix, then any real number times A is a Hermitian matrix. And Ka is a skew Hermitian matrix if K is purely imaginary. So if A is a Hermitian matrix, any real number times A is a Hermitian matrix, any purely imaginary number times A is a skew Hermitian matrix. So let us see why this is. So if A is a Hermitian matrix, that means A transpose or A conjugate whole transpose is equal to A. So if this happens, let us see what we can say about Ka. So now, what is Ka whole conjugate whole transpose? So Ka conjugate by the property is K conjugate times A conjugate whole transpose. That is nothing but K conjugate times A bar whole transpose, that is equal to K conjugate times A theta. K conjugate times A theta, but A theta is equal to A, so this is K conjugate times A. So if A is a Hermitian matrix, then what can you say about Ka whole theta? So Ka whole theta is K conjugate times A. And if K is a real number, then this is equal to Ka. If K is a purely imaginary number, then K conjugate is minus K. A similar conclusion can be drawn for skew Hermitian matrix also. So if A is a skew Hermitian matrix, then Ka will also be a skew Hermitian matrix if K is a purely real number and Ka becomes a Hermitian matrix if K is purely imaginary. So you can do a similar derivation as you have done here. So A is a skew Hermitian matrix, so A theta is equal to minus A. Now what can you say about Ka whole theta? So Ka whole theta is K bar times A theta as we have derived. Now K bar is equal to K if K is real minus K if K is purely imaginary. So A theta is minus A, so this is equal to minus K conjugate times A. Minus K conjugate times A. So if K is real, so this becomes minus Ka, which makes it skew Hermitian. So if K is purely imaginary, you get another minus, which is equal to plus Ka if K is purely imaginary. So if K is purely real, then Ka is also skew Hermitian. If K is purely imaginary, then Ka is the normal Hermitian matrix. So this is the first property which is very important to understand. The next property is that if A, B are two Hermitian matrices, if A, B are two Hermitian matrices, then lambda 1 times A plus lambda 2 times B. So any real number times A plus any other real number times B will also be a Hermitian matrix if lambda 1 comma lambda 2 belongs to real numbers. So if A and B are Hermitian matrices, any linear combination of A and B is some number times A plus some number times B will also be a Hermitian matrix, provided that the numbers are real numbers. And a similar property can be applied for skew Hermitian matrices also. That is, if A comma B are skew Hermitian matrices, then lambda 1 times A plus lambda 2 times B are also skew Hermitian matrices for all lambda 1 lambda 2 belongs to real numbers. So this is the second property with respect to Hermitian and skew Hermitian matrices. Let's go to the third property. So if A and B are again Hermitian matrices, AB plus BA is also a Hermitian matrix. So if you have two Hermitian matrices, AB plus BA is also Hermitian, and AB minus BA is a skew Hermitian matrix. So if you take two Hermitian matrices, then AB plus BA will be a Hermitian matrix and AB minus BA will be a skew Hermitian matrix. So this and this both happen if A and B are Hermitian matrices. So this is very easy to understand. So let us take A and B as Hermitian matrices, that is A theta is equal to A and B theta is equal to B. Now what is AB plus BA whole theta? By definition, this is AB theta plus BA theta, and AB theta by reversal law is B theta times A theta plus A theta times B theta. But A and B are Hermitian matrices, so this can be written as BA plus AB, which is same as AB plus B. So AB plus BA whole theta is same as AB plus BA if A and B are Hermitian matrices. A and B are Hermitian matrices. Now, if A and B are Hermitian matrices, let us look at this. What is AB minus BA whole theta? This is equal to AB theta minus BA theta. This is equal to B theta A theta minus A theta B theta, which is equal to BA minus AB, which is equal to minus of AB minus B. So AB minus BA whole theta is minus of AB minus B. Hence, AB minus BA is a skew Hermitian matrices. So A and B are two Hermitian implies AB plus BA is Hermitian, AB minus BA is skew Hermitian. So the next property is, so if A is any square matrix, if A is any square matrix, take any square matrix, A times A theta and A theta times A are both Hermitian matrices. A times A theta and A theta times A for any square matrix. So these two matrices are Hermitian matrices. So this can be very easily understood. What is A theta whole theta? By reversal law, this becomes A theta whole theta, which is A times A theta. A theta whole theta times A theta. A theta whole theta is A times A theta. So A theta whole theta is A theta. Hence A theta is Hermitian matrix. And for any square matrix, A plus A theta is also a Hermitian matrix. A plus A theta is a Hermitian matrix, and A minus A theta is a skew Hermitian matrix. So this can also be understood very easily. So what is A plus A theta whole theta? This is same as A theta plus A theta whole theta is A. So A plus A theta whole theta is again equal to A theta plus A. Similarly, A minus A theta whole theta is equal to A theta minus A, which is minus of A minus A theta. So for any square matrix, A plus A theta is a Hermitian matrix, A minus A theta is a skew Hermitian matrix. Now, using this property, what we can do is, so every matrix A can be expressed as, a sum of a Hermitian and a skew Hermitian matrix. So A can be written as A plus A theta by 2 plus A minus A theta by 2. So A theta gets cancelled, you get A again. So this is a Hermitian matrix, this is a skew Hermitian matrix. So every square matrix can be expressed as a sum of Hermitian and a skew Hermitian matrix.